today's lecture, we're going to be talking about the definition of computation and algorithms, something we've been leading up to a little bit over the last few lectures. And it's essentially mostly due, or the best versions are due, to this fellow, Alan Turing, one of the heroes of computer science, who Anil mentioned in the first lecture. Okay. So these are the questions we want to ask. What is computation, or what is an algorithm? And how can we really mathematically define these concepts and reason about them? And one reason we want to really have a clear definition of what these things are is so we can actually say, what is the set of problems that can be solved by computation. And in particular, we want to look at the question of whether, the definition you make for computation affects what problems turn out to be solvable. Okay, so just to remind you of some terms from last time, a problem is a technical term. It's what we try to solve with computation. And it's a mapping of instances to solutions. Instances or inputs to solutions. And we can generally represent these things conveniently with strings. So you can also think of a problem as a function that maps a string, the instance, to another string, the solution. Okay, and some examples of that are the multiplication problem, where the instance is a pair of numbers and the solution is their product, or sorting a list. We also like to concentrate a lot on this special case of a decision problem. It's essentially without loss of generality. A decision problem is just a problem where the solution is either yes or no, or true or false, accept or reject. Okay, so we saw some examples of decision problems from the last time, like primality. Given a number, is it a prime number? Palindrome, given a string, is it the same as its reverse? This is one we talked about last time. And I'd like to remind you that in the case of a decision problem, you can also think of it as equivalent to a language. Remember, a language is a set of strings. And given a decision problem, the corresponding language is just a set of all strings that are yes inputs. Okay, or conversely, if you're given a language, you can think of it as a decision problem where the input is a string and you're trying to decide if that string is in the language or not. So this is one very interesting language we studied last time. It's a simple language, just all the strings that consist of some number of zeros followed by the exact same number of ones. We'll call it 0 to the n, 1 to the n. And that was an example of a language that couldn't be solved by a DFA. Here's one that could be solved by a DFA. It's a very simple language, the language of all strings that have a length divisible by 2. Here's one more problem, actually a decision problem that's quite important in computer science, and we alluded to it when we were studying propositional logic. Satisfiability. Here the input is a propositional formula, which you can represent by a string. And the task is to decide whether or not it's satisfiable. Okay, so this is actually seemingly a pretty computationally expensive problem to solve, but you can solve it. Okay, so these are problems. These are what we want to try to solve by algorithms. And now let's finally try to ask, what is an algorithm? So we started with this sort of very wimpy model of computation, deterministic finite automata, and said that, okay, any problem that it can solve or any language it can solve, we'll call a regular language, some terminology invented in the olden days. But we also saw that there's some computational problems, like 0 to the n, 1 to the n, that can't be solved by DFAs. So they're not inside the regular languages. And we didn't show this, but it's also true that you cannot solve primality with a DFA. Let's say given a string which represents a number in binary, check if it's prime. That was almost on the homework, but didn't quite make it. Satisfiability is another example that you can't solve with DFAs. But all these things you could solve with, algorithms, at least according to what your naive or intuitive concept of an algorithm is, right? I mean, if I said, is there an algorithm to check if a number's prime, you'd say, yeah, you could just go through all the numbers 2 up to that number and see if it divides evenly into the given number. Or, I mean, this one's quite easy. Just count the number of ones, count the number of zeros, check if they're the same. Here, we know there's some algorithm, right? I mean, count the number of variables. Let's say it's n. Write down a giant truth table with 2 to the n rows. Fill it all out. Check to see if at least one of the outcomes was true. So we like to think that all of these problems can at least be solved by algorithms. The only question is, the one we're facing today, what exactly are we going to mean by an algorithm? Well, one thing you could say is like, I'm used to programming in my favorite programming language. Maybe that's Python. Actually, it's not my favorite programming language because I'm like an old person that doesn't understand these new things. But it's a popular one. And you might say, well, I can at least say I can solve all these problems with Python, right? I mean, let's take this 0 to the n, 1 to the n, because it's probably the easiest. I mean, there it is. It's an algorithm, right? I don't know. I constructed this by myself, but I didn't test it. I hope it's correct. But anyway, I mean, even if it's wrong, I think you can be convinced that you can tell if a string that's, the input to a function in Python has equally many ones and zeros. If you just got a string, you can like put your finger at the beginning and put your finger at the end and check that you see 0, 1, and then move them in and check that you see 0, 1, and move them in and check that you see 0, 1. OK, there's any number of ways to do it. Here's a simple little way to do it. OK, back in the olden days when I was in college, actually, I guess you guys maybe also studied C in an earlier class. So I mean, C is some other programming language. And you can equally well solve this problem in C. It looks a little bit different, but the concept is the same. OK, great. So we could say that these are all problems that you could solve with Python. And here's a question that we're facing. Maybe we should just define algorithm to mean like a function written in Python. Is that a good definition? Why not?
Yes, Python is that powerful than Turing.
The person said Python is less powerful, and then he said another model of computation. Well, we'll see about that, actually. Any other comment? I mean, anybody else want to offer an answer? Yeah?
What if the problem is interpreting Python code?
What if the problem is interpreting Python code? Well, could you write a Python program to interpret Python code? Yeah, actually, we're going to say you can, actually. Any other answers? Yeah?
Algorithms existed before Python.
Yeah, that's true. Algorithms existed before Python existed. It doesn't mean that this wouldn't be the best way to define it, though. I mean, I don't know, like number theory existed before we had like notation for it. But like when Euclid studied it, all his numbers were lengths of lines. So it was like very annoying, and we came to a better definition. So maybe this is a better definition. Any other comments? Yeah?
If we like suddenly decided to break Python, then suddenly we don't have any algorithms.
Yeah, if they decided to break Python or somehow it went away, we wouldn't have algorithms anymore. That's true. It's a bit weird that like it's sort of defined by to define it by like a programming language that happens to be kind of popular now. Well, actually, before we get to that, one thing that maybe wasn't mentioned, it's a kind of a technicality, but I want to say it now at the beginning, is this. In real life, if you're going to use Python, right, it's running on some real computer. And we like to define problems to be mappings from strings to strings, inputs to outputs. And we just say the input is some string, and that means it could be of any finite length. It could be length 10, 100, 1,000, 1,000,000. And in life, at least, these instances would be stored in memory. But maybe in memory, you couldn't have like a string of length 2 to the power 1,000, even though that's a finite length. But it's just nicer to assume that we have unlimited memory. In fact, we're going to need to if we're going to imagine running it on any possible input string. So you might not consider that realistic. Maybe it actually even depends on your computer model. I don't think in principle there's anything wrong in Python with being able to access unlimited memory. Maybe in practice it wouldn't work out. But it just somehow wouldn't be mathematically natural otherwise, right? I mean, it wouldn't make sense to say like, OK, an algorithm is anything written in Python, but it's only allowed to use at most 1 gigabyte of memory. That just somehow wouldn't be mathematically natural, right? There's a famous quote attributed to Bill Gates from 1981 saying that 640,000 bytes ought to be enough for anyone. Well, that's not really true. First of all, it's an apocryphal quote. He didn't actually say that. But also, it doesn't make sense mathematically, I think, in the context of algorithms to put any finite upper bound. So really, maybe we should add a little bit of an asterisk here saying, when I say Python or some other programming language, I'm also assuming you have an unbounded amount of memory. OK. So to get back to this question, there was some negative sentiment, I think, about whether this is a good definition. Actually, I kind of want to say it's not such a bad definition. We're going to argue, sort of, towards the end of this class that it's kind of an OK definition. It's not great, but it actually has exactly the right intuition. And if you just forget every technical thing we do in this class and kind of take this as the definition, you'll actually be thinking about the right concept. OK, so there's actually nothing too mysterious about what we're going to mean by algorithm. It really is going to end up being, anything that you could, compute with Python. OK, still, there are some downsides as a formal definition, some of which were mentioned or suggested. One of them is it's kind of arbitrary to fix the programming language, maybe like Python, like why didn't you choose C, or why didn't you choose Java, or standard ML, or what have you. So that's one kind of unnatural aspect of the definition. Another unnatural aspect of it as a formal definition is we'd really like to rigorously define these things. And even C, which is considered to be a pretty basic language and not have too many features, is very complicated. Like if you look at the official international standards definition of it, it's like a 700-page document just to define like the rules of C. Okay, and Python I don't even think has an associated document. It's kind of defined by what it is. So that's going to make it a little painful to reason about it formally. So OK, let's try to take these downsides and maybe come up with a better formal definition. So let's start with this question. Why not C or Java or SML or something like that? Well, we talked about a few random computational decision problems here and argued, yeah, you could write an algorithm to solve them in Python. I think if you knew another programming language like C, you'd probably also agree that you could also solve these problems in C. So one thing I want to ask you now is, do you think this is a real Venn diagram in the sense that it has 3 distinct parts? Are there things that you can solve with Python that you can't solve with C, or vice versa? Anybody say yes or no? Yeah? OK, we have one vote for the same. Anybody want to take the opposing position? You have to be a little bit careful, right? I mean, if you have some other programming language, like, maybe that programming language has the ability to like emit music tones on the computer or something, but that's not what we're getting at here. We're only interested in what computational decision problems it can solve. So it's a very basic thing. We only ask about, given some string input, can it get the correct yes or no output? So yeah, actually, I claim to you that these are not distinct sets. The set of things that the set of decision problems you can solve with Python is exactly the same thing as the set of decision problems you can solve with C. So here's the intuition for this proof. Well, one intuition for it is, our shared experience in programming. And I'm going to actually appeal to this a little bit throughout the class. I mean, I could just kind of say, right, there doesn't seem to be anything that you could do in Python that you couldn't write in C and vice versa. That's just an intuition, though. Let's go to a proof of this claim. Well, I kind of put proof in quotes, right, because this has some 700-page definition. This maybe doesn't even have a definition. But I think this will be a very convincing proof, I hope it is, that Python and C can solve the exact same set of decision problems. So we want to show that 2 sets are equal, this one and this one. So we always do that in 2 ways, right? We show that one set is contained in the other. And conversely, the other set is contained in the first set. And that shows they're equal. That's how a proof goes. So I want to argue, let's say first, that anything that you can solve with Python, you can also solve with C. And I think the following is a very convincing argument. The standard Python interpreter is written in C. So I mean, almost by definition, right, it has to be true. Suppose you write some Python program to solve a problem. How could you write a C program to solve the same problem? Well, in the worst case, you could hard code it, into the, you could take your Python program, write a C Python interpreter, hard code the Python program into it, and just have it execute the Python program. So I think that's pretty convincing. The second proof is essentially the same thing, although it's maybe not quite as convincing, but I claim it's pretty clear you could do the reverse. You could write a C interpreter in Python. I mean, Python's pretty good, right? You could write a C interpreter that just goes through all the lines and executes them. So I think that kind of makes the claim pretty compelling. Let's talk a little bit more about interpreters, because that's an important concept. So let's say we're doing a Python interpreter. So a Python function or program, right? It's just it's a piece of code. It's like a .py file. It's just some text. In fact, you can just think of it as a really long string, right? So what's a Python interpreter? What that means is some algorithm which you write in any programming language, maybe, that takes two inputs, okay? P, which is a piece of Python code, which you can represent as a string, and X, which is another string, which is like the input that you want to run the code on. So the interpreter takes two inputs, the Python program and the string, and it should just step-by-step simulate what would happen if you ran that code on that string. Okay, that's what we mean by an interpreter. So I mean, Python, it's got a lot of different instructions. It'd be quite intensive to write a Python interpreter, but evidently somebody did it, right? Apparently also they did it in C. So you can write a Python interpreter in C, and you can write a C interpreter in Python. That's why we kind of felt that C and Python can decide exactly the same languages. You can write a Python interpreter in Java. You can write a Java interpreter in Python. You can write a Python interpreter in ML. You can write an ML interpreter in Python. Okay, so it kind of shows that all of these programming languages can solve the exact same set of computational problems. You can write a Python interpreter in Python. This was mentioned before. You could do it, right? And the last one's kind of interesting. This would be called a universal Python program. Okay, you happen to write it in Python. Takes two inputs, a piece of Python code, and like a real input. And the universal Python program just simulates this code on that input. Okay, so I'm appealing a little bit to your intuition as a programmer that this can be done, but I hope you agree that you can, in fact, do it, perhaps laboriously. Okay, so that's kind of cool, because I hope it makes you agree that if this giant circle here is supposed to represent all the languages or all the decision problems you can solve with Python, then it's the exact same as all the problems you can solve with C, the same as all the problems you can solve with Java, etc. So that says there's something really cool and nice and natural about this set of languages. This is somehow a very natural set of languages or decision problems, and we'd really like to find a really good definition that encapsulates it. Okay? We kind of want to define this to be the set of problems that can be solved by algorithms. And we kind of have like a intuitive or somewhat unsatisfactory definition. Okay, but we want to come to a really satisfactory definition. Any questions so far? Okay. So we talked about this, and we at least kind of know now that we know what definition we kind of want to, we know what we want the answer to be, the set of all programs that you can solve with Python, but how to rigorously define that. We're going to come to this question now. It's a painful question because, even a simple-ish language like C has an insanely complicated formal definition. So now one thing you could say is, well, let's go down to an even simpler language that, even simpler than C. Any suggestions? What? Assembly, yeah, that's actually a good suggestion that I'm going to talk about. Assembly language. C not? Yeah, actually, that's a good start. Let's go down to, just as suggested, assembly language or bytecode. They're more or less the same thing. I guess many of you took 122, so you have some familiarity with exactly this. There was some bytecode defined, which is sort of like the assembly language that C0 programs got translated into. It was called C0 VM. It's a good start, right? I looked at it. The definition for that took like 14 pages. So, it's better than 700 pages. if you don't know what I'm talking about, like, or you don't know what 122 was, just think of it like assembly language, like, x86 assembly language. Okay, so this is what actually all high-level languages end up getting translated down into. So for that reason, I think you can agree it's still okay that whatever you can solve with assembly language or whatever you can solve with this C0VM, whatever you can solve with, let's say, C, you can also solve with assembly language or C0VM, because actually the C program gets translated into this simpler language anyway. Okay, and an assembly language is very basic programming language where maybe you have a few registers and like you have some memory that you can access. There's maybe like a heap and a stack. And there's like a very limited set of instructions, some basic arithmetic instructions and like go-to instructions and ifs basically. So it's a really, really simple language, simple enough that you could define it in 14 pages. So that's a good start. It's still pretty complicated though to reason about. So it'd be nice to have some kind of like really totally minimal programming language, like even way more basic and stripped down than assembly language. Like let's even delete more features from even the C0VM, make it as simple as possible. So let's say you might want to imagine some totally minimal or TM programming language that should still be powerful enough that we can argue that it can simulate bytecode or assembly language, because then we would know it could also simulate C and Python and kind of any natural programming language, but it's hopefully also simple enough that we can reason about it completely, mathematically, rigorously. Okay, so that's what we want to do. So let's try to invent one. Okay, so let's try to talk about inventing this totally minimal TM programming language. So it's going to be a ridiculously simple programming language, which is all about manipulating strings. And what I'm going to eventually do is, through examples, show that it's actually more powerful than it looks at first. You can really do a lot of basic programming tasks with it. In fact, I'll eventually argue that it's powerful enough that you could even simulate like some C0VM or some assembly language with it, and therefore also all of C and Java and everything. Now, you could actually not just claim this, but prove this, at least if you had a formal 14-page definition of your bytecode. We don't have time to prove this rigorously. Like in some earlier drafts of this lecture, I was really trying to sketch a whole proof, and there wasn't time. So I can really just only appeal to your programming intuition, but it's a fun thing to think about like at home when you're snowed in potentially in your dorm room, just how you could take this really minimal TM programming language and start to build up subroutines and stuff so much that you could really simulate some assembly language or even Python. Okay, so actually this TM really stands for Turing machines. It was a model of computation invented by Alan Turing in 1936 when he was a graduate student. Okay, he didn't call them Turing machines, he called them A machines, but it was a really heralded definition. People got very excited about it, and so now we call them Turing machines or TMs. Okay, so let's kind of warm up through the definition of Turing machines. Okay, so they're kind of a bit similar to DFAs, and there's a bit of a funny thing, right, where you can start thinking of like Turing machines as like the general programming language concept, and a particular machine M is like one piece of code. See, in the olden days, in like 1936, they didn't have the idea that you could build like one computer and run different software on it. They thought that you had to build like a new machine for every different problem you want to solve. And in fact, it was really Turing's 1936 paper that awoke people to the ideas that you don't have to do that. But still, historically, we'll call, you talk about a specific machine, but you should think of that as like a piece of code. So unlike DFAs, they're going to have access to memory. So this was really hampered DFAs. They couldn't like read and write. They could just read in a straight off line. And we're going to abstract the memory as like an infinite sequence of cells. And again, it was the olden days. They were thinking about physical machines, so it's called, for historical reasons, the tape. Like it was thought to be like a piece of paper. So here's the picture. That's the memory that the Turing machine will have access to. And you can number the cells, let's say, with the integers. Okay, so a machine takes as an input, so that's some string over an alphabet sigma. And it's assumed that the input is written on the tape to begin with, starting at position 0. Okay? All the other cells or squares contain this special thing, this cup shape, which means blank. Okay, so blank is like another symbol. I won't draw it like emptiness. I'll draw like an explicit blank symbol. And in general, in a Turing machine, the cells contain symbols from another alphabet called the tape alphabet, which I'll write gamma. So gamma should contain all the input alphabet symbols, sigma, and it should contain blank, because you're allowed to have blanks. And you can also specify at the beginning that has more symbols too. And that sometimes helps you design a Turing machine to imagine that there's a few more symbols you can use. By the way, this definition is kind of, it's totally minimal as we can get, but still a little bit complicated. So if you have any questions, just pipe up. OK. And somehow the Turing machine, or this code, accesses the memory through a pointer that points at the memory cells. And again, historically, it was considered like a physical object called the head. So we're going to call it the head. It's like a tape pointer, and it starts out initially pointing at 0, the leftmost character of the input. OK, so that's sort of the setup. Now, what is the Turing machine, or what does the Turing machine piece of code really look like? Here's how it could have been defined. And it might have been a little bit nicer had it been defined this way, but it's not quite defined like this. But if you, just think about this, you'll get more or less exactly the right idea. So think of it as a sequence of instructions, just like in a programming language or an assembly language. But there's only like, 6 instructions, basically. There's an instruction to move the tape head left, one to move it to the right. There's one to write a symbol, A, for any tape symbol in the tape alphabet. So really, that's one instruction per tape alphabet symbol. And there's basically like the assembly language jump if 0 or jump if whatever instruction, OK? It's like a combination of an if and a goto. So it does an if the head is reading some particular symbol A, then go to step J. OK? And you can have that instruction for any tape symbol A and any line number, if you will, J. And finally, these Turing machines are supposed to process their input if they're solving a decision problem and either accept or reject, just like DFAs. So we're going to have a halt and accept instruction and a halt and reject instruction. Yeah?
Why is, for the go-to instruction, why can't J be 0? Why is there the restriction that it has to be at least 1?
Oh, I guess didn't make it clear. I imagine in my head enumerating the n instructions 1, 2, 3, 4 up to n. Yeah, but maybe, maybe I shouldn't have. Maybe it's traditional here in 251 to number them 0, 1, 2 up to n minus 1. But yeah, you can go to any of those steps. OK. So this is basically it. As I said, it could have been defined this way, but instead it's defined traditionally a little bit differently, which is hard to say if it's better or worse. But anyway, we're going to go with the traditional definition. And the traditional definition, or maybe Turing's original thought process, was this. I think he was trying to simplify. He said, you may as well move the head at every step. If you want to move it, great. If you don't, well, you could do a left and then a right. So let's just assume that the head is going to move on every step. And he also said, you may as well also just write a symbol at every step. He kind of wanted to get it down to one instruction, is the idea. Because if you don't want to write a symbol, then just write the same symbol that you're reading. It's effectively like not writing a symbol. And you also may as well do a goto at each step. I mean, if you didn't want to do a goto, then you could go to the next line. And this one actually makes it a little bit more complicated, but really he was again trying to sort of get everything down to one kind of instruction. So he said, instead of having like a separate if for each possible symbol that the head could be reading, you could just have like a big switch statement or a case statement where you do a different thing depending on all the possible symbols that could be underneath the head. So long story short, in the traditional definition, like all the operations are boiled down into like one big kind of instruction. So let's say you have a Turing machine, and let's say hypothetically the symbols that you can write on the tape are A, B, C, and blank. So in the Turing machine definition, you again could think of a Turing machine as having a sequence of steps, S1 up to Sk. I wrote a K here and N on the previous slide. I'm not sure why. Where every step looks like this. It's a little bit complicated, but in some step, like step 13, you do a big switch based on what is currently in the cell where the tape pointer is, where the head is. If it's A, then write C, move the head left, and go to line 10. If it's C, write blank, move left, go to line 13. Okay? Every step looks at what's in the cell, chooses what to write into that cell, which way to move the tape pointer, and what line to go to next. And you should also have two special lines that are just the accept and the reject line. Okay? I'm going to give you some examples. In fact, you could even change this up a bit. See, now there's like a go-to in every single step, right? So before you thought of the instructions as like a list of instructions because you had in your mind that the typical thing would just be to go through them in order, maybe with some like occasional go-tos. But now if there's a go-to in every single step, there's no point really in imagining the steps to be ordered. So we call them states instead of steps. And in each different state, you can again think of like a line of code. The TM takes a different action depending on what symbol the head is reading. So it's really a lot like DFAs, right? Where you have a bunch of states, and then sort of what you do next depends on what character you're looking at. So in the DFAs, it has this read-only memory, and it always just ticks to the left. In a Turing machine, like lots of stuff is happening. The tape head is going back and forth. It's changing the symbols. But what it does next depends on what symbol it's reading. And then we generally draw Turing machines like DFAs. So here is like an official picture now. Finally, we get to the official definitions of a Turing machine. Okay, so it looks kind of crazy. In this example, the input alphabet is A and B, so it's trying to decide things about strings of A's and B's. And the tape alphabet, it's just going to be A, B, and blank. So it's got states. This one has 5 states. And as you can see, each one, or most of them, have arrows coming out of them, except for the accept and reject state, which have no arrows coming out, because those are the halting states. And let's look at what these arrows say. Let's look at this one, for example. This means that if you're reading A, if the head is pointing to a cell that contains A, then write a blank into that cell and move the tape head to the right. Okay? And then also it's an arrow, so it tells you what state to go to next. Okay, and you can see that for all the states, other than the accept and reject ones, of which there are 3 here, Q0, QA, and QB, they should have exactly 3 arrows going out, one for each tape alphabet symbol, one for each symbol that the head can be reading. So here, if you're in state Q0, you see an A, you do this step. If you see a B, you do this step. In particular, you write a blank, move the tape head to the right, and go to state QB. Or if you see a blank, you do this step. I'll now run through this example, but any questions? Yeah?
Why do we have to move left and move right?
It's a good question. Why do we have to move left and move right? Well, you could have maybe just move right. I think, in fact, we haven't finished the homework yet, but I think on the homework you're going to study what happens if you only had the ability to move right. This is a bit more like a DFA, where you can sort of only tick through the memory in one way. But it seems like for full power, you want to be able to go back and forth looking at different part of the inputs at different times. So there's 2 different parts. The statement was there's a go-to step anyway. You can imagine there's really like 2 different parts. There's the tape, which is like the memory. And there's this sort of finite logic, which you can kind of think of like the code, the instructions. And there's really, in some sense, 2 pointers. Where you're looking at in memory, where the tape head is, and what state you're at. And the memory pointer is the one that moves left and right along the cells. And sort of the instruction pointer sort of hops around the different states. I'll give an example now, which hopefully will clear it up. So let me show you what happens when you run this Turing machine on this input string, AABA. So as I said, you have this memory. It's an infinite list of cells. And the input starts out on the tape. This is position 0, and everything else is blank. So we start at state Q0. And, the initial state has this arrow coming in from nowhere. And what do we do next? Can somebody say or guess?
Q sub A and write it empty.
Yeah, exactly. So you look at what cell in the memory you're at, A. So you follow the arrow that starts with A, which is this one. And that tells you to write a blank into this cell and move the head to the right. So that's what we're going to do. Put in a blank and move the head to the right. And now we got into this state, QA. So, OK. What's the next thing that will happen? What state will we go to next? Yeah, so right now, we're looking at symbol A, so we're going to follow the A arrow, which is this one. And that tells us to write a blank into this square, move the tape head left, back here, and go to this state, Q accept. OK, so that was the tape action. And now we go into the accept state. And now the program halts. OK, there's no outgoing arrows. This is an accept state. And like with DFAs, maybe you can draw the accept state with a double circle. And the reject state is the state which doesn't have any outgoing arrows or a double circle. OK, so now the Turing machine computation ends, and we accept. OK, let's do another example. Let's say the input is this ba. So it gets written onto the tape cell like this, the beginning. The tape like this, the beginning. We start the pointer here, the tape pointer here. OK, we start in Q0. And what will happen? Well, we're reading a B, so we follow the B arrow to this state. We write a blank, and we move the head to the right. OK? Now we're in this state. We're reading an A, so we follow this arrow. And we write a blank, and we move the head to the left. So we'll do that. And now we get to the reject state, and the decision is reject. Okay, so this machine rejects this string. So you see it's a bit more complicated than a DFA. Can anybody kind of say overall what it's doing? I mean, this is already kind of complicated to just stare at it and see what it's doing. Yeah?
Accepting all strings that are either A or B.
Let's start with A or B.
Yeah, that's actually correct. This one accepts all the strings that start with the same two first letters. Well, you can kind of see what happens here. Is it, OK, if it starts out with a blank, meaning the input string is empty, then it immediately goes to reject. Otherwise, it kind of goes to the state which is named after the first character it read. See, if it reads A, it goes to the A state. If it reads B, it goes to the B state. And then you see the next thing that happens is, if it reads the same character as the state it's in, it accepts. And that would be the second character. Otherwise, it rejects. Okay, so if you've never seen this before, then it might be a little bit too quick for you to agree to what I just said, but you can study it after class. So let's call that particular machine that we just saw M. And what does it do when the input is some string x? Well, what we just argued, or I told you, is that if the length of the string is at least 2, and the first two symbols are the same, then it accepts. And it rejects otherwise. So if the length is less than 2, or the first two symbols are different, it rejects. It also has some side effects, which don't affect the accept or reject, but they do affect how you might use this as a subroutine in another more complicated program. You can in fact check that it always blanks out the first two cells, whatever they were, and it almost always leaves the head at the end in position 0, except if it's the empty string. So you can also check to yourself that this is true if you study this machine later. OK, I'll give you some more examples, but let's put up the official definition of Turing machines. And I think it should really remind you of the official definition of DFAs. OK, so if you really want to formally define it, and I show you this not because we work too much with this definition, but just to show you that you could really mathematically, rigorously formalize it. Has 7 parts, a set of states called Q, an input alphabet, which is another set of symbols, sigma, that's what the input words are written in, gamma, which is a tape alphabet, which contains all the input symbols, plus blank, maybe plus some more symbols. Has a start state, an accept state, and a reject state. And again, the most complicated thing is this transition function, which encapsulates all the information written on the arrows. Particularly, you can think of it as a big table of information where for each state that the machine might be in, and each symbol that the head is reading, might be reading, it maps it to the new state, this is sort of the go-to part, the new symbol to write in, and whether or not to move the head left or right. Yeah?
So a Turing machine can only have one accept and one reject state?
Okay, good question. The Turing machine can the Turing machine only have one accept and one reject state? Because that's a bit different from DFAs. It depends on your definitions. And actually, every textbook might define Turing machines a little bit different. But for us, let's say yes, it only has one accept state and one reject state. And it's kind of okay, because if you wanted to have multiple accept states, then you could just make one big accept, just like one real accept state, and have them, all your desired accept states, go to it in the next line. Okay? That's something you couldn't quite do with DFAs, because DFAs had a very rigid structure where they only had one time step per character. But here you can do little tricks like this. Very good question, though. So this is the official definition of what a Turing machine is. We could also write the official definition of how it computes, but that would be like probably 2 or 3 more slides, and I'm not going to do it. It's just what you expect, though. It's what I explained in words, okay? I do want to emphasize one extremely crucial difference compared to DFAs. Okay, and this is maybe the most interesting thing. Well, one of the most interesting things is that a Turing machine might never halt. A DFA always halts. It runs for a number of steps exactly equal to the number of characters. But a Turing machine might never halt. And this is just the same as with usual algorithms, like Python or C or whatever. Sometimes you write a Python program that just goes into an infinite loop and never halts. That's a simple example. So let's see an example of that. Now, this Turing machine that we talked about before, I didn't quite prove it, but it's not hard to show that it halts on every input. Kind of all the arrows are sort of going down, just kind of explains why. In fact, it always halts in at most 2 steps. A Turing machine with this nice property that it halts on every input is called a decider. It's the decider Turing machine. And we really like deciders. Okay, they make us happy. You don't like when your program can get into an infinite loop. That's kind of like it crashed. So let's see an example of not a decider. Say we take this Turing machine and make a very simple change. Let's take out this arrow and change it to be a self loop. So now let's see what happens. Let's say this input is the empty string. That's a valid input. So there, all the tape cells are going to be blank, including the tape cell 0. So now you start at state 0, and you see a blank. So you do this loop. You write another blank, and you move the head to the right. Well, that's also going to be a blank. So you're going to do this loop again. You're going to write a blank and move the tape head to the right. And it's also going to be a blank. So it'll just tick off like this forever. The tape head will keep moving to the right. You'll keep writing blanks, and it'll never halt. So it's kind of like a trivial infinite loop in Turing machine language. This is a technical term. If M running on some input X never halts, we say that it loops. And here, M running on the empty string loops, so M is not a decider. Okay. So now, let's make a definition. A language R is said to be a decidable language, or also computable. Those are synonyms. If there's some decider Turing machine M, such that every string in the language, M running on that string halts and accepts. Every string not in that language, M running on that string halts and rejects. Okay, so it's like DFAs, but you really, where we called this regular, but you really have to worry about this issue of whether or not it halts. In fact, here, these two conditions already imply that it's a decider, because this says for every string, it either accepts and halts or it rejects and halts. But I really want to emphasize, you're only deciding a language if you're always halting. Okay, and we use the same notation as for DFAs. If we have a decider Turing machine, M, then L of M means the language of all strings that it accepts. Sometimes in like textbooks and things, they'll still define L of M to be all the strings that a Turing machine halts and accepts on, even if it's not a decider. But let's not do that. Let's really say that if M can ever get into an infinite loop, if it's not a decider, then we don't say it computes anything. Okay? So that's why when we're designing Turing machines, we always want to make sure that they always halt. So we saw this language back when we were talking about DFAs and regular languages, 0 to the n, 1 to the n, which was not regular. No DFA can decide this language. And what I'd like to show you now is that it is decidable. It is computable. There is a TM that decides it. And it's really going to be quite like that idea of checking for a 0 at the beginning, a 1 for the end, then moving inside, checking for 0, 1, moving inside, checking for 0, 1, etc. So here it is. I'm not going to go over this exactly, but I strongly encourage you to look at it later and convince yourself that this works. It's not too complicated. I'm going to try to, this is a little bit cheap, but I'm going to try to explain in words what it's doing without saying it very rigorously, to try to give you the idea, for the interest of time. So here's the picture. This is the tape. And let's imagine what that Turing machine I drew is going to do on this input. 4 zeros, and then it's almost 4 ones, but it's got a 0 in here. So actually, this string is not in the language. It's kind of close, but it's not in the language. So anyway, it goes onto the tape as the input. Everything else is blank. The tape head starts here. And then we have this set of states up here. So what is the logic of these set of states? Well, the first thing it does is, if the very first symbol is blank, what does it do? Yeah, it goes to the accept state. If the very first symbol is 1, what does it do? Yeah, it goes to the reject state. Actually, I can show you. If it sees a blank, it goes accept. If it sees a 1, it goes to the reject. Otherwise, it kind of gets started. It says, OK, we got a 0. Great. Oh, one thing I didn't mention here is, here the input alphabet is 0 and 1. For my Turing machine, my tape alphabet is going to have 0, 1, blank, and I'm going to take the liberty to have another symbol, pound. So this has 4, hashtag maybe, I don't know. This has 4 tape symbols. OK, so if it sees a 0, it kind of gets started. And what it does is it writes down a pound to sort of mark, like, OK, I saw this 0. And then it goes into some other logic thing that just does a very simple kind of loop that keeps walking the tape head to the right as long as it sees 0 and 1. And then it does something the first time it sees a blank. And what does it do when it first sees a blank that takes it to another little bit of logic here? It goes back to the left one. And here it really checks if it's reading a 1 or not. If it's reading a 0, it rejects. But if it's reading a 1, then it's kind of like, all right, good. It had a 0 at the beginning and a 1 at the end. It writes a pound, which kind of checks it off. And then it goes into a little logic loop that walks back sort of to the beginning of the string, where it sort of now interprets blank and pound as the same thing. So it kind of walks back until it sees, well, pound. And then it goes into some other little logic piece that says, OK, once you see the pound in the walking left step, go to the right one. And now it basically starts the algorithm over again. So it kind of basically goes back to the initial state. In fact, I think it literally goes back to the initial state Q0. That's this arrow. And it does the same thing. So it kind of checks this off. It rejects if it's a 1. If it's a 0, it sort of checks it off, walks to the right. OK, got to the right. Oops. When you get to the right, go back 1. Check that this is a 1. check it off, go back to the left. Oh, we got to the left. Check off the 0, go back to the right. OK, we got to the right, check that this is a 1. Oh, wait a minute, it's not a 1. So we reject. OK, and if it eventually checks them all off, it accepts. So again, that was a little bit fast, and I didn't really go through all the states. Again, there's only sort of so much time in this lecture, but you should really go home and study this exact diagram up here and see that it's really doing this logic, and that it decides this 0 to the n, 1 to the n language. Yeah?
Why did we need a pound symbol?
Why do we need a pound symbol? You're saying we could have used, let's say, blank instead? Yeah, we might have actually been able to use blank instead. Yeah, we could have. I think. I didn't totally double check it. But actually, it illustrates a little bit one technique that we'll see later, which is it's quite helpful to add flexibility by having more than one character, or more extra characters. You can kind of use them to remember things, or maybe mark the tape cells in a different way. That's a good point, though. I think you could have gotten away without it. Yeah?
So are there problems that require you to have additional characters in your tape alphabet?
Great question. Are there problems that require you to have additional characters in your tape alphabet? We'll talk about it later. Long story short, no. Is that a question?
Can you have arbitrarily many?
Can you have arbitrarily many? Yes, but it should be finite. So at the beginning, you have to say, here's my finite tape alphabet, and here's the code that goes with it. Although, we'll see it doesn't matter that much. There's a lot of little tweaks you can do on Turing machine definitions, and they're all eventually equivalent. That's actually why it's quite a nice notion. Here we had a tape that has two-way infinite memory. A lot of times it's defined as just having a one-way infinite memory, where the cells are indexed by natural numbers rather than integers. Turns out one can simulate the other, so it's not a real difference. And there's a similar thing with the tape alphabet. Any other questions? OK, so as it turns out, Turing machines are like a cool programming language. Literally programming with them is kind of tiresome. Every computer scientist, though, should spend some time in their life doing it. It's really illustrative, and it helps you understand computation. Unfortunately for you guys, that time is now. So this is that time in your life where you're going to spend some weeks, maybe even a month, because there's a midterm eventually, thinking about Turing machines. So, just like any programming language, there's some tricks you kind of learn as you start programming in it that makes your life easier. And you can develop subroutines and stuff like that. So again, I would love if I had more time and I could show you how to do each of these tricks, but I only have so much time to kind of tell them to you. It's kind of like a hint, and you should go home and really think about how you would really do it. So here's a very basic trick, the trick of moving all the way to the right until the first blank is encountered. So the Turing machine doesn't even know, at first, how long the input is, but it can go into some little loop that does this technique and get at least to the end of the input. And we kind of saw basically that in the 0 to the n, 1 to the n Turing machine. Now, in that, the simplest way to do that, you write the same character you're reading every time, so it doesn't change the input. But one thing you could do is, you could have a little lag in what you write versus what you read. So you could read the first symbol, and like in the very first Turing machine, remember with the two characters equal thing, you kind of went into a different state depending on what symbol you read. So you kind of you remembered that symbol, and you could write it the next time. And that will have the effect that it not only moves to the end of the string, it actually shifts the whole string one space to the right. So that's a nice trick. And in fact, after the end of these slides, it'll be posted online. You'll see a Turing machine that does that. It's kind of like a bonus example for you to study. Once you can do this, then you come to this trick. This is an extremely useful trick. It's to take the input and space it out. Insert a space between every character. And you can kind of do it by combining these things. You first shift the whole input to the right, then walk back until you see a space, and then go to the right again, then shift the whole input to the right again, starting from the second character, and then come all the way back, go 2 more steps to the right, shift it all to the right again, and repeat that. And after some logic, 4 or 5 states, you'll get to this string. Now why is this a good idea? It gives you a little bit more space to do some computation. And in particular, one thing you can do is, imagine your tape alphabet is just 0, 1, and blank. But you really wish like you had a couple more symbols, like pound. Well, you're allowed to actually just say, like, OK, I have a finite alphabet gamma, so I can just include pound. But actually, if you want, you could simulate it. And the way you could do it is first take your 0, 1 string, space it out like this, then go back and fill in all the blanks with zeros. So instead of each cell being 0, 1, now each pair of cells is like 0, 0 or 0, 1. And now you can have your Turing machine kind of think of each pair of cells as a single big cell. So that takes a lot of logic, and maybe it sort of doubles the number of states or something. But now it's like 2 cells count as 1 cell, so you could also have 1, 0 and 1, 1. And now it's kind of like you got an alphabet of size 4 plus blank. Again, it's a little bit fast, but it's more like a hint. You should go home and try to think a little bit more about that. So this actually kind of explains why the exact definition of what tape alphabet you're allowed, how big it is, doesn't really matter that much, because you can even simulate it by a little tape alphabet. You can actually even do it just with 2 symbols, like writing everything in unary. That's very annoying. OK. Another good trick, which is a little bit like this pound sign trick, is to mark cells. What does that mean? Let's say your tape alphabet is 0, 1, and blank. You just say at the beginning, you know what? I'm going to have 0, 1, 0 with a dot, 1 with a dot, and blank. Or you can simulate that if you want. And this is a good trick, like if you're moving the head around, and let's say you want to remember, like the head was right here, but now I want to go do some other logic, but eventually come back to where the head was. What you can do is say, OK, if I'm reading a 0, I'll replace it with 0 dot. So I still think of that as a 0, but it lets me like move around for a while, and then eventually go to some piece of logic that sort of like walks right until you see a dot. So it kind of lets you remember where a tape where the tape head was at some other part of the computation. Again, it's kind of like a hint that you can use to when you're doing some TM programming practice. Once you have this, you can do like kind of cooler things. Like you can copy a stretch of tape from one, let's say, marked location to another marked location by sort of shuttling the head around to look for the marks. Now you're really starting to get more powerful. Like you can implement some basic string operations like reverse a string, or arithmetic operations like increment a number written in binary. This is a powerful one. You can actually simulate a Turing machine with 2 tapes by maybe interleaving the tapes. You can implement like a dictionary data structure by appropriately copying strings around. With this, you can sort of simulate random access memory. And this is like maybe a key step if you really want to show that Turing machines can simulate C0VM or assembly language. Because they're like, in assembly language, usually you have some like indirect memory lookup where you like write the address of a tape cell, and then you kind of automatically get the contents of that cell. If you want to simulate that, you kind of need some kind of data structure for the memory. You can do that too. Okay, and with enough time and practice with Turing machines, you'll eventually discover that you could even simulate like any byte language, and therefore you can simulate C and Java and everything. So honestly, again, it would be cool if we had like a whole lecture where we just programmed stuff in Turing machines and had a lot of fun, and I could really prove this to you. But well, we don't want to take up that much time. So I hope your programming experience makes you kind of believe this. OK, so the conclusion is that any algorithm written in Python or C or whatever can be simulated with the Turing machine. Actually, we didn't even talk about efficiency, but if you're a little bit smart, it's not even that inefficient. OK, so now we can finally come back to the beginning of the lecture and the philosophical place where we started, where we wanted to define rigorously the set of all problems that could be solved by algorithms. And we kind of agreed that this was a good definition, like everything you could solve with Python or C or whatever. And now we can also say this is the same as everything you can solve with Turing machines. which we also defined to be decidable. That's just a terminology. And that's quite satisfactory because it solved the problem that these things are impossible to define. C took like 700 pages, but a Turing machine, took a couple of slides. So in particular, if you can kind of write any program with a Turing machine, one thing you could write is a Turing machine interpreter with a Turing machine. Same as a Python interpreter. You can think of a Turing machine as just a piece of code. You can, usually we draw it with circles and stuff, but you could use that 7-tuple definition to really convert a Turing machine into a string in some reasonable format. And then you could write another Turing machine called U. That's called a universal Turing machine, which takes as input the description of a Turing machine and an input string and simulates that Turing machine on that input. You can even actually, in the literature, you can see how to do it with some simple machine with like 10 states. So just to repeat, a universal Turing machine is a Turing machine or an algorithm that takes as input a pair, M, the description of some other Turing machine, and X, like the real input string, and U simulates M of X. In other words, U of M of X is just going to simulate exactly what M would do on X. In particular, it'll accept if M of X accepts, it'll reject if M of X rejects, and it'll loop if M of X loops. So, if M of X gets into an infinite loop, then U of M of X will just keep simulating it. Okay, so that's a very important concept, and in fact, it was one of the great theoretical ideas in computer science from Alan Turing's 1936 paper. So if you don't believe me, you can literally go to like page 14 of his paper. He has like 2.5 pages where he literally draws a universal Turing machine and proves that it has this behavior. And what's pretty cool about that is here I kind of convinced you that by a lot of appeal to your knowledge of programming, your experience programming in Python and Java or whatever. In 1936, there were no electronic computers. And in fact, at the time, if you said computer, they would say, oh yeah, you mean a person. That was the definition of computer back then, a person who was trained in following calculational directions. These are some pictures of computers from Turing's time. You'll notice they were essentially all women. Do you know why that is? It's because, there's no inherent, a man and a woman can compute equally well, but it was the olden days and very uncivilized times, and you were allowed to pay women less back then. So they're like, well, if it doesn't make a difference, I'll cheap out. So this is what computers looked like back then. Great. So that's the definition we want to make about algorithms. But it's important maybe to close by asking a few questions about this definition. So here's a question. Could there be a reasonable definition of algorithms that computes more languages than these languages? In other words, more languages than those that are computed by C or Python or whatever. Any thoughts about this? Any suggestions? Yeah?
No one knows.
No one knows. Yeah, kind of. Actually, it's a little bit difficult to say whether you could know the answer to this because in some sense it's about a definition, but on one hand we do have some kind of natural conception of what an algorithm is, so maybe someday tomorrow somebody could think of like maybe a more powerful language or something that can compute more languages. On one hand, it's a little hard to imagine though, right? Like suppose somebody tomorrow said, oh, I invented a language that's even cooler than Python, like Python++, and it can solve a lot of problems. You kind of know in advance like that it's not going to solve more problems, right? Because that person had to like write the compiler for Python++ in some other language that we know of. So again, you could probably simulate it. In fact, if you look at Turing's 1936 paper, he makes a very similar argument talking about computers, i.e. the people. And he really says like, okay, we're trying to define what is computation. So computation is what a computer, i.e. a person, does. And you should really read his paper. He takes like 4 pages towards the end to say like, okay, let's imagine a computer. She's in there. She's trying to solve some problem. Let's give her like an unlimited amount of paper and a pencil. And what can she do? She can write down symbols. She can like move her head like this. He has like a long section about how like the human eye. He argues that it can only distinguish finitely many different symbols, which is why he says it's okay that the tape alphabet is finite. He has some argument about why he thinks the brain can only be in finitely many different states, which is why he thinks you can only have finitely many states. He kind of justifies this by saying, well, you should imagine that the computer could always like take a break. And so then she has to write down what she was doing before she goes to take a break and come back. And that writing down what she was doing is really like writing down a state. But she only has finite time in her life, and there's only finitely many symbols, so she can only write down finitely many states. So it's actually a pretty cool philosophical argument for why Turing thinks the Turing machine captures all notions of computation. I recommend you read it sometime. Okay, so when he made this proposal, actually in the 1930s, there were several other people thinking about the definition of algorithm, mainly because of this Hilbert and Scheitung's problem, which wanted to ask, is there any kind of mechanical algorithm for telling if a sentence is valid, in a formal logic sentence is valid? And so people were like, okay, we better define algorithm. And Gödel came up with some definition, but he really was like, I'm not satisfied with this definition. This person, Kleene, came up with a definition. Post came up with a definition kind of similar to Turing's. Church invented lambda calculus, and he like took a strong claim, like this should be the definition of computation, but people didn't really buy it. And when Turing published his paper about Turing machines, like it was very philosophically compelling, and that argument about a human computer was compelling, and like it's just made it so easy to think about computation that people really accepted his thesis quite early. And it came to be known as the Church-Turing thesis, and it says this. In fact, Anil mentioned it in the very first lecture, that any natural or reasonable notion of computation can be simulated by a Turing machine. So this is not a theorem. You might ask, is it just an observation? Is it a definition? Could be. You could just say, this is my definition of algorithms, Turing machines. Is it a hypothesis? Is it a law of nature or a law of physics? Anil also in the first lecture mentioned this physical Church-Turing thesis, which is a bit more concrete. It said sort of any notion of computation that can be carried out in the physical world can be simulated by a Turing machine. Maybe that's a bit more concrete than this one about definitions. You might ask, is it a philosophical statement? Okay, these are all interesting questions. Anyway, I don't know. It is what it is, and essentially everyone believes it. Actually, a little bit later, we'll talk briefly. You might think that the notion of randomness, which actually arises in nature due to quantum mechanics, could affect this thesis. It really doesn't, though. You have to be a bit careful about what you mean for a randomized algorithm to solve a computational problem. But when we eventually talk about that in the latter half of the class, we'll even really see that randomness or quantum mechanics don't really challenge this thesis. Okay, so this is the set of all languages that we're finally kind of going to be satisfied with. It's all the problems that you can solve with Turing machines. We call that decidable. We really kind of tried to argue that it's all the languages you could solve by any algorithm. And if you believe in the Church-Turing thesis, then that's really true. So let's ask one more question. If you go back to this circle, is there anything out here? Is there any language which is not decidable, solvable by any algorithm? Well, in fact, Anil will tell you about the answer to that question on Thursday, because it was also answered in Turing's paper. Wait, I have 10 more slides. No, I'm just kidding. It's over. The TAs seem to have the quizzes. How can they get them back? Recitation or?
Yeah, they'll be sorted by recitation. They'll be like A on this side, B, C.